Good. Okay, we're good now. All right, sure.
Order, because for example for this cycle A has to come before B, B has to come before C, and C has to come before A, which is impossible. Let's move to the code. We first need the recursive function to
Subjavis.
C has to come before A, which is impossible. Let's move to, because for example for this cycle A has to come before B, B has to come before C, and C has to come before A, which is impossible. Let's move to the code. We first need the recursive function to perform the depth-first search traversal. It takes as parameters the graph. For this cycle, A has to come before logical sort works on directed acyclic graphs only. A graph that has cycles can't have a topological order, because for example for this cycle, A has to come before B, B has to come before C, and C has to come before A, which is impossible. Let's move to the code. We first need the recursive function to perform the depth-first search traversal. It takes as parameters the graph, the actual vertex, the set of visited vertices, and the stack. We first set the actual vertex to visited, then we visit every neighbor. To do so, for each neighbor, if it's not visited, we recursively call the function on it to visit it. After doing so, as explained earlier, all the vertices whose the actual vertex is a prerequisite are in the stack. We can push the actual vertex. We are sure that it will come before its neighbors in the ordering. And we also need a non-recursive function where we create a stack, the set of visited vertices, and we call the recursive function on every unvisited vertex. After it, we create an array ordering and we keep popping from the stack and inserting in the array until the stack becomes empty. Then the recursive process.
Okay, let me go back to that video again.
And then E and D can go next. And topological sort is the ordering of vertices of this graph such that for every edge UV going from U to V, U should always appear before V in the ordering. So for this graph here, one topological sort could be A, B, C, E, D, F, G. Another ordering could be B, D, A, C, E, F, and G. So the point here is that C should never be before A and B.
That makes sense. Yeah, I guess the order doesn't matter because it's, I guess, about kind of the levels nested of the path, like the level path. A and B are both on level, I guess, 0 or 1, depending on what you start at. C and D are in level 2. So I guess in that sense, BD or AC, I guess it doesn't matter. It's a little interesting how BDA is valid. I guess so, because AC and BD are not really, I think, interconnected maybe.
In the ordering, or D should never be before B, or E should never be before C, and so on. So one of an application of topological sort is in the build system. Suppose these were the packages of a build system saying that C has a dependency on A and B package, and D has a dependency on B, and E has a dependency on C, and so on. So how would the build system know that which package it should build first? So what it does is it builds a graph of the packages and then applies a topological sort on them, like create one of this ordering, and then builds the packages in this order. So A and B build first. So C has dependency on A and B. So then C can go next, and then E and D can go next, and F can go next, and G can go next, and so on. So in the next section, let's see how we're going to do topological sorting. So we have two data structure, a set and a stack. Set has all the visited vertices, while stack has all the vertices in topologically sorted order. So what we're going to do is we're going to start from any node. So let's say we started from E. So first thing we do is E is not in the visited set, so we put E into the visited set. So we put it here. Then we are going to explore the child of E, children of E. So we go in the direction of H. So H is not visited, so we put H into the visited set. And then we will explore the children of H. H has no children, it means that H has been totally explored. At that point, we put it into the stack. So only when a vertex has been totally explored, it means that all its children have been explored. At that point, you put that vertex into the set. So we put H into this stack. Then we go back to E, and then E has other child F, and F is not in this visited set. So first we put it into this visited set. And then we go to F, and then F has a child G. So, and G is not in the visited set. So we first put it in the visited set, and then go to G. And then at this point, G doesn't have any children. So G is done exploring G, so we're going to put G into this sorted stack. So we'll put G into this stack, and then we go back to F, and then F has no children, no more child to explore. So we're going to put F into the stack, and then we go back to E. At this point, E has explored all its children, so we're going to put E into the stack. So now, what we're going to do is we're going to pick any another vertex which is not visited. So let's say we picked B.
Okay.
So first thing we do is we put B into the set. Then we
Explore C and then D, but then we've seen E and F already, so we don't need to go farther at that point.
a child of B. So let's say we picked C. C is not in the set, visited set. So we're going to put C into the set and explore the children of C. C has one child E, and E is already in the visited set, so we don't do anything. And then C has no other child. At this point, we put C into this stack. And then we go back to B. B has another child D, and D is not in the visited set, so we put D into the visited set. And then we go to D, and D has a child F, which is already in the visited set, so we don't go there. And we stay at D, and D has no more child to explore, so we put D into this stack. And then we go back to B. At this point, D has explored both his children, so we are done exploring B, so we put B into the stack. And at this point, let's pick another unvisited node. So the only unvisited node at this point is A, so we go to A and put A into this visited set, and then explore child of A, which is C. C is already in this visited set, so we don't do anything about it. Come back to A. A has no more children to explore, so we put A into this stack. So at this point, this stack has topologically sorted order of vertices of this graph. So it's A. We call elements one by one from the stack A, B, D, C, E, F, G, H. Remember, there are multiple topological sort orders possible for this graph. It's just the order in which you pick this vertices, decide which one of them will show up. But all of them have this property that if there's a vertex U and V going from U to V, U will always show up before V in this ordering. So in the next section, let's quickly look at the code. So the main function is top sort. In this
I mean, it makes sense. I get what a topological sort does now. Makes sense.
Hey everyone, welcome back.
And welcome back to the cracking thing. Children of a cycles will screw us up, and then we just need to be able to visit every single course. Like, it could be the case that a course just isn't visitable, and therefore you can't take it. So what we need to do is we just need to make sure that we can, visit all the courses. So we just want to check that our DFS can actually just touch every single node. So that's essentially what we're going to do, but we're going to use it, do it in a topological sort manner, just because we can apply the code to course schedule 2, and another question called alien dictionary, which can actually be solved in the exact same way. So 3 questions for 1 algorithm that's basically the same code. Sounds like a perfect combination to me. So hopefully this part wasn't too confusing. What we want to do now is actually go to the code editor, and I'll walk you through it line by line. I understand that this part can be a little bit confusing. Drawing it out is like a huge mess. Instead, let's actually just walk through the code line by line, and it should be a lot clearer if you just listen and watch me code, and as opposed to me trying to draw this out, and it's just gonna be horrendous. So let's go to the code editor. That's enough blabbing. We are back in the code editor. Let's type this up. The first thing I want to check is actually that prerequisites is not empty. If it's empty, that means that there's no prerequisites, therefore we don't have to worry about not being able to take courses. So append the prereq to it, right? Simple enough. Presets in prerequisites. We want to essentially say self.graph for a given course. We want to append the prereq to it, right? Simple enough. Now, gray set is going to be all of the nodes that we're currently have a black set, which is also, and let's define them and talk about. We typically do a 3-set approach for solving a topological sort problem. So there's 3 sets, and let's define them and talk about each one. So the white set, and we're going to initialize it to all of the keys of our graph. So self.graph of keys. We're going to have a gray set, which is going to be empty, and we're going to have a black set, which is also going to be empty. Now, let's talk about what each one of these sets represents. So the white set represents all of the values that we still need to process. So basically, you can think of this as kind of like our work queue. This is the number of nodes that we need to process in our graph. The gray set is going to be all of the nodes that we're currently processing. Remember that in this depth first search, we get to a node and then we want to fully explore its children. Now, what happens when somewhere along the dependency chain of its children, you actually end up at the node that you started your search from? That would indicate a cycle, and this is what the gray set aims to prevent. When we're
I see.
processing a node, we're going to put it in the gray set, and if somehow down the line in the DFS we actually end up at that node again, then that means that we have a cycle, and therefore we simply exit out because this problem is not solvable. We have a cycle. The black set is going to represent all of the nodes that we have fully visited, and when we say fully visited, we mean that we have visited it and all of its.
Huh. That's the way he solves it. How does Leetcode solve
Hey
it?
everyone, welcome back. Let's write some more. We have our prerequisite map, so we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1. We see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that that for adjacency list, and I'm going to call it prerequisite map because the data structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2. And we're going to repeat that for every single course. So for 1, we know that 2 does not have any prerequisites, so we can just put an empty list over here. 4 also does not have any prerequisites, so we get another empty list. So now we're going to run depth first search on every single node. I'm going to do it in the order from 0 to n minus 1. So be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map, so we're going to do it recursively. We see that it has two prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1, we see that it has two neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor, 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that this is empty. So what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3, and we see that it only had one prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also a course that can be completed. And so what we can actually do is from its prerequisite list, we see 4, we can just remove the 4. We know it can be completed. And so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed. So I removed the only prerequisite that 3 had. Then from 3, we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed. And then from the 3, we're going to end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know
Imagine being able to build anything, for any reason, in any style, at any scale.
4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now I'm going to go back to 0, which is how we even got to 1 in the first place. And we look at the prerequisites of 0. We see 1 is no longer a prerequisite because we basically know that 1 can be completed. But we still have to look at this 2. So then we're going to go to the last unvisited node in our entire graph, which is 2. So now we've gotten to the last course.
Two different approaches, but I don't know which one's better.
And welcome back to the Cracking Fang YouTube channel. Today we're going to be solving Leetcode problem 200. So we're going to say course x value, put it in the gray set, and if somehow down the line in the DFS we actually end up at that node again, then that means that we have a cycle, and therefore we simply exit out because this problem is not solvable. We have a cycle. The black set is going to represent all of the nodes that we have fully visited. And when we say fully visited, we mean that we have visited it and all of its children fully. So if we ever get back to a node that's currently in the black set, we can simply just stop the search there and move on to the next value because it's already been fully explored. There's no reason to do it twice. So those are your 3 sets. Now we need to process all of the nodes in the white set. Excuse me. So let's now process the white set. So we're going to say while white, so while we have something in the white set to process, we want to get a course out of it. So we're going to say course is going to equal to white.pop. So we're going to pop some random course from the white set. And remember that ordering doesn't matter here. All we need to do is just make sure that we can actually visit all of our courses. So we're going to pop a course from the white set, and we're going to go into our DFS function. So we're going to say if not self.dfs, and to this DFS function, we're going to pass the course, we're going to pass the gray set, and we're going to pass the black set. Now, what this function DFS is going to return is true if basically we can visit all of the children successfully, and false if there's a cycle. So if this function ever returns false, that means that we have a cycle and we can simply stop there. This problem is not solvable. So if our DFS function returns false, obviously not false is going to be true. So this is going to evaluate. So we simply return false here, right? Otherwise, we simply continue. And if we're able to process the entirety of the white set, which means that we're able to basically reach all of the nodes in our dependency graph, that means that we're able to take every single course and we're good to go. We can simply return true. Now what we want to do is actually define the DFS function. So let's define it. So we're going to say def DFS. We're going to pass self. We're going to pass the course that we're processing, the gray set and the black set. The first thing that we want to do is we are now visiting course. So we want to add it to the gray set. So we're going to say gray.add course, right? Because that indicates that we're processing it. If we now end up back at this course, then that means that we have a cycle and we can return false. So remember that, we want to visit all of its children now. So, for a course, we want to start visiting its prerequisites, and we want to make sure that we can do that. So we're going to say for prereq in, so remember, self.graph for that course. We're going to say if that prereq is in the black set, then we can simply continue, because remember, the black set represents nodes that we have visited entirely, which means that we visited it and all of its children. So if we've already visited that node in its entirety, then we do not need to visit it again. So we can simply just continue to the next node in our kind of list here for that course. Now we also want to check whether or not the prerequisite is in the gray set. So we're going to say if prereq in gray, then we're going to be returning false here. And the reason for that is, remember, the gray set represents courses that we're currently visiting. So if we're currently already visiting this prereq as part of our DFS, and we somehow end up at it again, that indicates a cycle. Therefore, we return false, because obviously cycles mean that we cannot solve this problem. If both of those conditions don't fire, then what we want to do is we want to go on to just performing the DFS. So we're going to say if not self.dfs, and we're going to pass in the prereq this time. We're going to pass in the gray set and the black set. And remember, this function will return false if there's a cycle and true if there's no cycle. So if we get to this point here where there is a cycle, and the reason for that is, remember, it's entire, we want to visit all of its children now. So, for a course, we want to start visiting its prerequisites. We want to make sure that we can do that. So we're going to say for prereq in, so remember, self.graph for that course. We're going to say if that prereq is in the black set, then we can simply continue, because remember, the black set represents nodes that we have visited.
Black means we're done. We've already processed it. We don't need to do it again. If it's in the gray, then we return false, because that means we were processing it, but we somehow ended up in a cycle. And then if it's white, then it's a new node, and we have to just DFS into that node, I believe.
Visited entirely, which means that we visited it and all of its children. So if we've already visited that node in its entirety, then we do not need to visit it again. So we can simply just continue to the next node in our kind of list here for that course. Now we also want to check whether or not the prerequisite is in the gray set. So we're going to say if prereq in gray, then we're going to be returning false here. And the reason for that is, remember, the gray set represents courses that we're currently visiting. So if we're currently already visiting this prereq as part of our DFS, and we somehow end up at it again, that indicates a cycle. Therefore, we return false, because obviously cycles mean that we cannot solve this problem. If both of those conditions don't fire, then what we want to do is we want to go on to just performing the DFS. So we're going to say if not self.dfs, and we're going to pass in the prereq this time. We're going to pass in the gray set and the black set. And remember, this function will return false if there's a cycle, and true if there's no cycle. So if we get to this point here where there is a cycle, we want to return false. All right. The last thing we need to do is, now that we have fully processed this course by going through the DFS here for all its prerequisites, the last two things we need to do is actually remove the course from the gray set, because it's now been fully processed. So we're going to say gray.remove course. We're also going to say black.add course, because now it has been processed and all its children have been fully processed. And since there was no cycle detected, we can simply return true here. And that's going to be it. So let's just run this, make sure we didn't make any typos anywhere, and let's submit it. So, oops, let me just open this up. And as we can see, it is successful. Apologies for the cutout there. I accidentally, when I first recorded the code, I said the wrong time and space complexity, so I just cut that part out, and I'm going to redo it.
Huh. Solution's a little bit different. Let's ask ChatGPT which one's better.
Hey everyone, welcome back, and let's write some more neat code today. So today let's look at a graph problem. Actually, it's called course.
Okay. Says Leetcode is better.
Schedule on the first neighbor 1, So now we look at 1, we see that it has 2 neighbors, 3 and 4. So let's recur. We need to empty. So check width of that, which is or which empty course, and the number of prerequisites is true. Every course is completable, and the time complexity for this is gonna be big O, the number of nodes we have, which is n. I'll use n as that, and I'll use p for the number of prerequisites that we had, because if you notice in this graph, we have to visit every single node, and we have to move along every single edge. And once we get rid of the prerequisites from here, we don't really have to visit a course twice, because once we know it can be completed, we can instantly do that. We don't have to go through its prerequisites twice. So I'm going to show you one last example. This is the example that what we're going to do. How are we actually going to detect this loop? Because we see, so I'm just going to cross this stuff out because we're looking at a different example. But here we see that 0 has a prerequisite of 1, 1 has a prerequisite of 2, 2 has a prerequisite of 3. So this is a loop. We cannot complete these courses. But how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure. And it's going to be a set. Though I think you could just use an array if you want. I'm going to call it the visit set. And all it's going to contain is the list of courses that we're currently visiting along our depth first search. So let's say we start at 0, then we add 0 to our visit set. We take a look at the prerequisites of 0. We see it has 1 prerequisite. So then we move to 1. So now we visit 1. So we're going to add 1 to our visit set. And we look at the prerequisites of 1. It has 1 prerequisite 2. So then we move to 2. We run depth first search on 2. So to do that, we have to first visit 2. So 2 is also going to be added to our visit set. And lastly, we see 2 has 1 prerequisite of 0. So then we of course want to visit 0. And so now we're going to visit 0 twice. But you see that 0 is already in the visit set. Therefore, we detected a loop. Therefore, we have to return false. These courses cannot be completed. So now let's finally look at the code. So the first thing I want to do is create our pre-map. So our list of prerequisites. Since we're going to do this recursively, I'm going to define a nested function, depth first search, inside of our canFinish function, because then we'll have access to all these variables without having to pass them in as a parameter. The only parameter that we have to pass in is the current course that we're visiting. And so like most recursive functions, we want to look at our base cases first. The first base case is if course is in the visit set already. So what this means is that we're visiting a course twice, so we detected a loop, so we can return false, meaning that this course cannot be completed. The other base case we know is if the prerequisites of this course happen to be an empty list. What that tells us is that this course has no prerequisites, and we can return true because it can definitely be completed. If neither of these conditions is satisfied, then we can take this course and add it to our visit set, because that means we are currently visiting this and we're going to recursively run depth first search on its prerequisites. So I'm going to loop through the prerequisites of this course.
You want to go to college, finish college, or jumpstart your career. Who says in order to go places, you need to travel.
For each one, I'm going to run depth first search on it. So depth first search on this prerequisite. If it happens to return false though, then we know we can return false immediately. We don't have to wait, because if we find one course that can't be completed, then we can return false for the entire function. So I forgot to put a not over here. So if not, meaning if it returns false, then we return false. But if this does not execute, that means it's a course that can be taken, and we want to return true in that case. But before we return true, we want to remove it from our visit set, because we are no longer visiting this. We've already finished visiting it. So visit, remove this course. And also, since we know this course can be visited, what we can do is say pre-map. We can set it to an empty list, so that if we ever have to run depth first search on it again, we will in that case execute this condition and return true immediately. We will not have to repeat all this work of running depth first search on its neighbors. So that's all for our depth first search function. The function is done. It's now have to execute this condition and return it again. We will in that case execute this run depth first search on it again, so that if map, we know this course can be visited. What we can do is say pre-map. We can set it to an empty list, so that if we ever have to run depth first search on it again, we will in that case execute this condition and return true immediately. We will not have to repeat all this work of running depth first search on its neighbors. So that's all for our depth first search function. The function is done. All we have to do is call it now, but we have to potentially call it for every single course in the number of courses that we have. And if any of them happen to return false, then we have to return false immediately. And if they don't return false, then we can return true. All courses can be completed. And the reason we are looping like this is mainly because what if our graph is not fully connected? Like, what if we have a graph like this? 1 has a prerequisite of 2, and maybe 3 has a prerequisite of 4. So these are two separate graphs that are not connected, right? So we have to manually iterate through every course and check, can 1 be completed, can 2 be completed, can 3, and can 4 be completed. So this is the depth first search solution. You can see that it does run very efficiently, about as efficiently as the breadth first search solution as well. And I hope this was helpful. If it was, please like and subscribe.
Okay. I guess let's start over then. So I think the whole gist of this problem, I guess to reiterate, is that we need to first build an adjacency list. And then we're just going to have to DFS and detect whether or not there is a cycle. We can use a visited set to determine whether or not there is a cycle or not. And yeah, I guess we're gonna, and that's it. So the first step is we have to build our adjacency list, right? So we're gonna have to go create a dictionary, which we'll just call this an adjacency list. And we're gonna default this because this will be all initialized as a list for the values. And then, so basically what we're saying is in order to take 1, you need to take 0, right? So I guess the order, I don't know, I feel like it's a little confusing this way, but when you write it this way, is this how it actually represented?
So we get another empty list.
0 points to 1, 0 points to 2. I guess that's just how it is. So 1 points to 0. So to be able to take 1, you first need 0, right? So sure, we'll leave it as is, and then it's not as intuitive, but it's okay. So for what do we call this? Could just do for A, B, and prerequisites. So from here we can just say adjacency list of A as the key, and then we're gonna append B, right? And that's it. That's it. So at this point we've built our adjacency list, and then the next step is really just to build our DFS function. And I guess maybe I would go through building the logic of what's the order of which I want to do things in, like how do we trigger our DFS, which is we go through all of the prerequisites. We have the number of courses, right? So num courses is our n basically. So we're going for range from 0 to num courses minus 1, right? Because in this example that we have a 1 and a 0, and the number of courses is 2, and it's 0 indexed, so it's num courses minus 1. So from here, we have we just have to run the DFS, right? We DFS I, and then also we can easily determine, so if at any point our DFS is failing, so if not DFS of I, we can just simply return false. And then if we get through all of these without any issues, then we can return true, right? So the next step is to build our actual DFS function, which is going to take C, I guess. We'll just denote C as the course. So let's first think about our base cases here. So in a DFS, our base cases are always going to be, in this case, if, we're also going to need to have a visited set, right? So we're going to need to have a scene set. So if C in scene, so this means that if the course is already in our visited set, that means we've detected a loop, right? So loop can return false here. Then the next thing is if adjacency list of C is equal to an empty list, right? This means that we have either nothing to process, or we've already processed it and then we overwrote, the prerequisites to a null array, right? So in this case, we don't have to process and redo any of our DFS because we've already gone through that node and processed it, right? So if we're not at either of these cases, we just need to visit it, right? So we'll add, so scene.add, we'll add C to the visited set. And from here, we're going to have to go through all of C's neighbors, right? So for nay in adjacency list of C, right? So this is saying once we've added it to our set, we're going to now check the adjacency list that we've built for the current course that we're looking at, and then we're going to go through all the neighbors. And then at this point, we will basically DFS for every neighbor. And in the same way, we're going to say if not DFS of nay, then we can simply return false, right? But if we've gone through all of this, we're chilling. So far, our processing is good. So after we process this, we're also going to need to remove this just to make sure that we've actually processed all of it. And then at the end of all of this, we can adjacency list of C and mark it as an empty list now, because we can basically mark it as we're done. We've gone through everything and there's nothing else that we need to process if we see this ever again. And I think that's it. Do we need to return anything? Yes, I guess we have to return true, of course, by the end of all of this. Otherwise, we're going to return nothing, right? I mean, this works, but I still feel like I struggle with DFS sometimes. Like, I don't understand why. I mean, I guess it all depends on like what you're returning in a DFS, right? Like, I feel like for any true and false DFS, I guess you're going to have these like, I guess if not, like whatever happens with the DFS, you can just end early. I'm guessing this is like a common thing. I mean, removing. So I guess I could ask, and let's just make sure. Can you explain why we need to remove from the visited set after we DFS the neighbors? So we mark that it's in the recursion path and then we remove after exploring its neighbors. I'm currently visiting C. I'm done exploring C. I'm leaving this DFS path, so it's safe to revisit in a different path later. That makes sense. Yeah, this makes sense. Okay, so basically this remove is basically saying that if we ever had, let's say, a case where we had something like 0 that goes to 1. I was thinking about doing course schedule today. What are the chances? And then we had 2, right? And then we also had 1 go to 3. So the thing is, right? We're gonna go to 0, right? And we're gonna add 0 to the visited set. Then we're gonna 1, then 1's in the visited set. Then it's gonna go to its neighbors as well. It's gonna go to 3, then it's gonna go to 2, right? But once 2 is finished processing, 2 is going to have no other neighbors, right? Because 2 is the end, basically. So it will hit this true case. So at this point, we'd return this returns true. Then it goes back to 1, right? And 1 is going to go, I guess, or actually, I think it goes back to 3. And then 3 is going to return true. And then it goes back to 1, right? So in both of these cases, we have not hit a false case, right? So we're going through all the neighbors, and then we're going to remove C from each of actually, we don't add 3 and 2. 3 and 2 are actually not in the visited set. I stand corrected, because if we do have an empty list, we actually don't process any of this logic, which I don't know if it's that intuitive, but okay, that makes sense, I guess. Which means that 0 and 1 are still in the visited set, right? So we go through all of these, and then we're actually going to remove C, which still technically doesn't make sense, because actually I think what would happen is, yeah, we processed 1, so actually we remove 1. So we added 1, we went through all of 1's neighbors, and then we remove 1. So we remove 1, then the adjacency list of 1 now is an empty list, and then we bubble back up to 0. And then from 0, we've also processed all of this logic, so we're going to remove 0. Now nothing's in the visited set, and then adjacency list is set to nothing for 0, which we can return true. And I guess this also actually applies to 1 as well. I don't know. I feel like DFS is not that simple. I don't know. I feel like I still don't have like an extremely good grasp of DFS. Not sure what it's going to take for me to like have it fully click. Maybe I just need to like grind a ton more DFS type of problems like this. But I always feel like DFS is a little bit iffy with me, like trying to figure it out on my own. I feel like it always makes sense when I look at the solution, but JSON creates an adjacency list, and then loop DFS through all of the courses. Okay. Which, I mean, I guess it makes sense. Not sure. Wait, this list is changing. It's a little sus. Now this question has been like bumped up a little bit. So 415, add strings, easy question. Please give me easy questions. I would like that. Given two non-negative numbers, number 1 and number 2 represented as strings, return the sum as a string. You must solve this without any built-in library. Okay. You must not also convert the inputs to integers. All right. Okay. You can't convert the inputs directly. Okay. They are non-negative though. How the hell am I supposed to add anything if I don't have any conversions? If I can't use when they say directly, I don't understand what that means. Does directly mean like I mean obviously I can't just be like 11 like int of 11 plus int of 1 2 3. But am I allowed to convert the single digits to an int? I mean I would assume that's a thing, because if that's the case we could just do 2 pointers, right? So from right to left, convert the character to an int, and I guess we can have a deck and append left, and then convert it to a string at the end. And this would be a potential solution, but I'm not sure if I understand if this is allowed. I mean, another thing we could do is, I mean, if we could process these numbers, which I don't know if is allowed either, we could just process them individually, right? So go through nums1, convert it to a number from right to left, and then go through nums2, convert it to a number, same way basically. We'd look at 3. We basically would mark it as a 3. I don't know. This question's a little weird though. I don't know if I like this question. This question's a little vague. Meta's asked this 15 times. I pray to God that I get easy questions on Meta. That would be like legit God tier. It's also crazy how two-sum has been asked on Meta. So that means there are candidates getting two-sum, which is, I think, wild to me. That's wild. That is wild. should I look at the solution? Do I want to look at the solution? I mean, I kind of want to code up, I guess, what my ideas are, just so that I can get some practice on, you know, just being able to code up my ideas. Now the thing is, I don't know what this means. All right, I'm gonna ask ChatGPT clarifying questions. I'm currently solving this, but I don't want the answer. I want to treat it like an actual interview, on-site interview, and want to ask clarifying questions. What's up, bro? I won't give you hints unless you ask first a few clarifying questions. Are both... Wait, what? No, don't be the candidate. You are the interviewer, bro. Okay. Okay. So when you say implements... Oh. You should implement the addition manually, digit by digit. Okay. So, I mean, that literally clarified it for me. Okay. So, yes, that is good. All right. So, if I can go through number by number, then I think I'm going to also assume that we're not allowed... I mean, I could just convert 456 and then add 77. I don't know if that's allowed. So, but I guess that's the same thing as just converting it to an int. So I think that's not what they're looking for. So basically, I think this solution doesn't apply. So I think my first solution is what they're looking for. So basically, we're going to have P1 is equal to length of nums of 1 minus 1, and P2 is equal to the length of nums 2 minus nums 2 minus 1, right? And so we finish this condition at any point, I think, if whichever ends first, I guess. I don't know if there's a cleaner way to handle it, but one of the numbers could end up being bigger. There's two scenarios, right? One of the numbers is bigger than the other, and then they can both be the same length, which in that case, we won't have any additional numbers to process. There's kind of like several edge cases we'd have to deal with. This question, I don't know if it's that easy, but I'm just trying to think if there's a better way to do it. So like, for example, if we have 4, 5, 6, and 77, right? We do have to handle edge cases, right? And this could also actually be like 9, 5, 6, right? Plus 77. So in this case, this is 3, right? With a carryover of 1, which is also another 3. In this case, so actually our while loop, I think, would stop in this case because now the P2 pointer has ended and the P1 is left, right? So I guess I would just do a 1 plus whatever number that we ended up with. Okay, yeah, that's not too bad. I think if that's okay, then I'll probably go with that approach. So while P1 and P2, and we will convert and then we're also gonna say I could just append it as a string and then reverse it at the end, right? I think that's not too bad. So we can just say res as a normal string. And we're basically going to say, and we need to have a carryover, which I think, let me just I think we're going to have this outside, initialize it outside the while loop. And we're going to have to convert these to an int, right? So n1 we're going to mark as nums. Oh, actually not nums, it's just num. So num1 of p1. And then just to make sure I don't forget, I'm going to decrement p1 and p2 by the end of this loop. So n1 is equal to n, and num2 is p2 of, and because it's a string, we're going to need to convert to an int. Int of that. And we're going to say cursum is equal to n1 plus n2, right? And the cursum could be greater than 10, right? So there's two cases. If the cursum is greater than 9, then we have to do the carryover, right? So, which we're basically going to say, I think we can simply say that digit is equal to the cursum modulo 10, right? So for example, if we have number like 13 modulo 10 would actually return 3, which is what we want. I believe that's how modulo works. Otherwise, we can simply just keep digit the same. Which actually in this case, and also we'll have to update carryover over is equal to 1. And also if it's in this case, we're gonna have to update carryover to 0. And in this digit, we have cursum. What's Leetcode? It's just basically, it's like the SATs for coding, basically. That's like the easiest way to describe it. If cursum is greater than 9, digit is equal to the cursum. And I guess I don't necessarily need digit, but do I want to say, I mean, cursum, I could just overwrite it. I don't think it's that big of a deal. And then here we can actually just res plus equals cursum, but we need to convert this to a string. So we're going to convert it back to a string, right? And at this point, we decrement our pointers, and let me just double check that this logic is sound, right? So we start, for example, at 1 and 3, right? So num of 1, so we convert it to an int. So this is num1 of p1, which is the last, p1 should be pointing to, in this case, 1, right? So it's 1, the second one. And then n2 is pointing to 3. So then cursum is equal to n1 plus n2, which is equal to 4. And cursum is less than 9. So, I should say less than, greater than 9, right? So cursum is not greater than 9, right? So we can say, we go to this else case, carryover is 0, which is fine. Oh, and I forgot. So it's actually curse sum modulo 10 plus the carryover, which I should say here, carryover. Yeah, so this is actually the way we should do it, because carryover is 0 because we just started, right? We hit 4 as our curse sum. We res, our res would now be currently equal to 4, right? And then we decrement our pointers down. So now we're looking at 2 and 1. So 2 and 1. In this case, our sum is 3. So we're going to append, skip all this stuff because it's all the same. And now we're going to decrement our pointers again. However, P2, okay, actually, I don't think that this check is valid. We need to say P1 is less than, or is greater than or equal to 0. And P2 is greater than or equal to 0. Because that is our actual exit case. And so at this point, we can say that at this point, right, we processed num1, which was already at 0. So when we decrement our pointer again, P1 is going to be -1. So we're going to break out of this loop. And so at this point, we'll say if P1 is greater than or equal to 0, then we're going to simply say or if P2 is greater than or equal to 0. I can't do an else because, you know, I need to check both. We can return res, but we're gonna have to return the reversed version of res. And let's see. The thing is, we need to figure out if we need to process the carryover, right? So this is 4 then 3. This is actually should be 4 then 3. This thing is, we need to add this 1, right? But nums, like, it could be way more than, one character. It could be like 3 characters. And if that's the case, we need to process the carryover to the, you know, the digit that we stopped on, right? So if carryover, then we're gonna need to say num1 of P1, say n1 is equal to int of this again, and we're just gonna say n1 plus 1, else n1 is equal to, actually, hold on, I'll say it like this. So n1 is equal just to the int of this. If carryover, then we're going to say n1 plus 1, else n1 is equal to else. Otherwise, we don't do anything, right? And then we'll just simply mark this as carryover is equal to 0, and we'll never see this case ever again. And we'll just res dot, or res plus equals string of n1. But there is a case though. So actually we still do process all this again. Oh, that's annoying. I guess. I don't know if there's a better way to write this, but there's technically a case where if n1 is greater than 9, then carry over is equal to 1. And otherwise, carry over is equal to 0. And technically, I think this whole thing applies to the second case as well. I'm just kind of copy and paste all this, just to make sure that we have all the variable names correct. And then I think this should do it. But this is a lot of lines of code and it's not very clean, which I don't like. I'm not a fan of. Okay, it doesn't even work. Okay, cool. Oh, that's right. That's right. Oh, that's right. So if I forgot one more edge case. If carryover by the end of all of this, if carryover res plus equals 1, and that's it. Oh shoot, let's do a 1. Alrighty. Why is this wrong? Oh wait, I feel like this is wrong. There should be plus carryover. And this should be plus... Wait, what? Hold on, this makes no sense. Should be n1 plus carryover. Or what the hell am I saying? n1 plus carryover. And then if n1, what is this logic? If n1 is greater than 9, then do all this. Okay, this looks correct. And then redo all this. P2, number 2, P2, n1, carry over, okay. Bro, what? How's this wrong? How the hell is this wrong? Why am I getting... So 9... Okay, so I start at 9, 9, right? Which is 8, which I add. Then I should be doing an carryover 1. Why do I have an extra 1? Set return res if carryover else 1 plus res. Is that different? No, it's the same. Oh, why? Why is it? I don't understand. N1. We're going through N1 plus the carryover. 18. Okay, so let's go through this case, right? So in this case, we have 9 and 9, right? So it's equal to 18, right? So 18 plus 0, because there's no carryover in the beginning, This is greater than 9. 18 is greater than 9. So curse sum, we overwrite it to 8, right? And carryover is equal to 1. So yes, 18. Now at this point, we'll say curse sum is equal to 8, right? It should be. That's my thinking is. And then we get out of this loop, right? And we check if P1's negative now, so we don't process any of this, but it's P2 now. So P2 is equal to 0. N2 is equal to the int of, which is 9, plus the carryover. So it should be 10, right? And 10, oh wait, maybe we don't need to care about carryovers. No, I think we do. I don't know how I'm supposed to handle the second case actually. Damn. The thing is, I don't like the second part. I don't know if this makes sense. Because we technically do need to be going decrementing this pointer. P2 minus equals 1. And then P1 minus equals 1. I don't even know how we're not. Oh, it's an if. It should be a while, I think. Assuming we have to go through every character. Okay, we passed way more test cases, but we still failed this test case. So why are we adding a 1 though? I don't understand where this extra 1 is coming from. But like, could I just add 1 to the ints that we have left? I don't know. I would, okay. Let me ask ChatGPT. Okay, so once we've processed, okay, let me speak this. Once I've processed all of the elements in num1 or num2, because I'm thinking about doing a 2-pointer approach from right to left, am I allowed to just add 1 to, num1 or num2 if there's a carryover? Or if there's not a carryover, I can just simply, add the rest of the string? Or do I still have to process each digit individually? You should process each digit individually. Okay, I will simulate it then, if that's what you want. That seems to be like what you want. So in this case, right, if we have this 9, we have this 9, 18, 18 is curse sum. We'll say 18, right? This is our first run through, which actually only goes through once. Carryover is set to 1. Curse sum is set to 8. So we should have 8. And then we'll say while P2 is greater than or equal to 0, right? So P2 is actually equal to 0 right now. And we're saying N2 is equal to int. So num of P2, which is 9 plus carryover, which is 1. So why is 9 plus 1? That's 10, right? But there's 2 edge cases though, right? If it's the last digit, you just don't confused. Dude, I can't even solve an easy question. This is pathetic. Can't lie. while p2 is greater than or equal to 0, n2 is equal to the int of num2 p2. If n2 9 plus 9. No. 9 plus... It should be 9 plus 1. Oh, I didn't modulo it, I think. I think that's why. Right? N1 is equal to N1 modulo 10. And carryover is that. I think same thing for this. Yeah, I think it got jank because I don't modulo it. I think that's our issue. That makes sense. Yeah. But is this really the ideal solution? I feel like, I don't know, there must be some sort of like jank, clever solution for some reason.
With Asana, the enterprise work management platform, tasks and company-wide goals are in one.
Hello, and welcome back to the Cracking Thing YouTube channel. Today we're going to be solving Leetcode problem 415, add strings. Let's read the question prompt. Given two non-negative integers, num1 and num2, represented as strings, return the sum of num1 and num2 as a string. You must solve the problem without using any inbuilt library for handling large integers, such as big integer. You must also not convert the inputs to integers directly. So for example, if we were given the number 456 and 77, we would want to return 533. Let's see how they did that. Let me change my pen here to be more.
Dude, this guy's audio is so trash though. Like, I don't understand why he doesn't just normalize his audio compared to like all other videos.
Okay, so we see that we have the number 456, and we want to add 77 to it. Well, if you remember from, I guess, elementary school, how to do addition, what we need to do is basically add these numbers and take care of the carry. So 7 plus 6 is going to be 13, so we have 3, carry the 1, 5 plus 7 is 12, plus the 1 that we carried, so 3. Then we carry 1 again, and then 4 plus 1, 533, which is what we can see as our answer here. So essentially what we've done here is we've lined up our values here, and we've added them. So we want to do the exact same thing for our strings. Basically, we want to align them and then go from right to left and add the values at whatever index. What you'll notice here that this string on top, the 456, is actually longer than 77. So what happens when we get here where there's nothing? Well, what we want to do is, if we're traversing and we're at an index in one of our strings that is not accessible because it would be out of bounds, then we would just want to treat that index as a 0. So if we just pretended that this was 077, then we could do the additions as much as we wanted. And this 456 could have any other.
That's clever. I did not think of it doing it that way. I guess if you do it that way, then it simplifies the logic.
Things in front of it, we would just treat those indexes as 0. That way we can just add directly and we wouldn't have to worry about anything. So that's the idea, that we're going to use 2 pointers, one to start here at the beginning, the end of our first string, and one at the other end, and we're just going to go from left to right, extracting the value at the current index. And remember that since we're going from right to left, we're going to be decrementing our index each time. So if the index for a particular string ever goes below 0, that means that we've exhausted that string entirely. Therefore, instead of extracting whatever value is at the index for that particular string, we're just going to extract the value 0. And that way we can just continue doing addition to parse through the longer string. And then we're going to have to maintain a carry variable here to, keep track of these carries that we had each time. And, we'll just do the addition each time and then add that to some sort of like string builder and then join it all back together so we can return our, result here as a string as it asks for. So that might be a little bit confusing, but let's go to the editor, and once you see the code, everything will be super clear. This problem is quite simple, and it does lay the foundation for some other problems on Leetcode, so definitely want to know how to set up this problem. But like I said, it's super simple. So let's go to the editor and see the code. We're back in the editor, and let's write the code. So like I mentioned in the explanation portion, we're going to want 2 pointers. One pointing to the end of num1.
I don't know. I mean, I don't modify the input array, but I guess the other solution is Facebook interviewers like this question and propose it in 4 main variations. The choice of algorithm should be based on the input format. Strings, integers. Usually the interview will ask you to implement a sum without using plus and minus. Oh nah. Bit manipulation? Are you kidding me? That is cringe. That is cringe. How the hell are you supposed to do it with bit manipulation? Oh my god, bro. What is this called? Some... Do they really ask this? No, like if they ask... I mean, Meta has asked this more than 6 months ago. Dude, I don't know. I feel like if you ask this question, like, what is being good at bit manipulation going to, like, really do? That's annoying. this string. This use school book digit by digit addition. Note that to fit into constant space, add binary. Sum of two binary strings. I mean, that's actually similar, I guess. Binary string is similar to what we just did. I think it's the same thing. I think I actually just solved it the same way. Oh, I see. Oh my god. Z-fill? I don't know about Z-fill. Like, come on, bro. I didn't know about Z-fill. Like, what the freak is that? Add strings. Okay. Arrays. Add array. The same textbook edition. Linked list. Okay, sure. What is this? What the hell is string builder? Res carry while P1 or P0. Oh, that's right. I don't have to do. I mean, it's a little tricky, I guess. Yeah. In Python, I guess you could gracefully. I don't really think about this as intuitively, but in Python, you can gracefully handle the cases, I guess. Carry. What is this? Why is divide floor division 10? I feel like you don't need to do it that way, but that works too, I guess.
One pointing to the end of num2. So let's declare those variables. So we're going to say I equals the length of num1 minus 1. That's the last index. We're going to say j equals the len of num2 minus 1. Now what we want to do is remember that we need to keep track of the carry. So we can add that each time when we do our addition. So we're going to say carry equals 0, and we're going to say res, which is where we're going to store our result here, is going to be an empty list. Now what we need to do is we need to exhaust both num1 and num2. So we need to move our pointers until we've done all the possible additions that we have. So we're going to say while I is greater than or equal to 0, or j is greater than or equal to 0. And remember, we're using or here because if they're both the same length, then it's really simple. They'll both end at the same time, so we're decrementing by 1 each time. But if one is actually longer than the other, it will take longer to reach its end. And then while that one is processing, the other one that has already been exhausted, we're just going to, instead of extracting the value at its index, we're just going to extract the value 0, because obviously adding 0 to anything doesn't change the computation. So with that explained, let's now extract the values we have at the I and j index. So we're going to say cur I is going to be the integer of num1 of I. And we're allowed to do this because remember
I guess I could just code that up real quick.
Does this sound familiar?
Oh my
You
God.
read about the curse
Bro.
type on Twitter. Want to give it a try?
We can't.
Ads. Okay. I think a lot of the solution can stay the same. I think these. Oh wait, sorry, this is wrong. Yeah, there's a lot of, I guess, a lot of unnecessary while loops going on, which is unoptimal. I think for the future, I need to somehow remember that, you know, Python has conditional statements that are built in that can make your life way easier, which I need to remember. For example, right? So in this case, I can actually look at it as, but why is this code so short though? I guess because the math is all just handled very gracefully, I guess. So while P1 is greater than 0, equal to 0, or P2 is greater than or equal to 0. So I guess now my thought process should be not just simply, you know, if one or the other. I should think about it in terms of when it's non-existent, then just mark it as a 0, right? There's no need to just leave the while loop. We can stay in the while loop, and if it's as long as one of them is greater than or equal to 0, we have something to process, right? So with that being said, we can say that num1 is equal to num1 of p1 if p1 is greater than or equal to 0, else 0, right? And then n2 is num2 of p2 if p2 is greater than or equal to 0, else 0. And the sum or recurse sum is equal to n1 plus n2 plus carryover in all cases, right? And then we can check if curse sum at any point is greater than, if it's greater than 9, then we have something that's that we need to carry over, right? And we can update actually our curse sum to be equal to curse sum modulo 10. And otherwise, if we don't, actually there should not be a 9, it should be a 1, else instead our carryover to 1. And at this point we can simply just res plus equals our curse sum, and at the end of all of this we can just do this logic. The hell? Did I not copy it? All right. Oops. Carry over equals 0. Oh, that's right. That's right. We need to convert this to an int. So need to convert that to an int and mark this in parentheses. Up, and yeah, I need to convert this back to a string, but it's okay. I would have known that. Oh, and I forgot to decrement my pointers, of course. Silly me. P1 minus 1 equals 0, P2 minus 1 equals, yeah, okay. Timeout, timeout. You can time this out. Okay, boom, boom. There we go.
Convert the entire thing to an if j greater than or equal to 0. So that's how we extract that one. But now we also need to keep track of the carry. So the carry this time is going to be, and do note here that we're so at this point, what we need to do is we need to decrement this. So we're going to say sure. So let's just submit this, make sure we have it. Our solution here is going to be, it's also.
Yeah, I mean, this problem is not too bad. I guess, okay, so yeah, I need to remember, I guess, like, this is just good practice. Like, if I ever do see a question like this, I'm going to need to make sure to, like, the trick of you can process both, even though they're not the same length. Be careful and make sure that you continue the while loop until both pointers are finished. You can still process one without the other by just marking by defaulting the value at 0. Okay, this makes sense. Your voice is echoing. Can you read my message? Is that true? Chat, is my voice echoing? I don't know. I don't know if anyone else is in my chat. I don't think I should be echoing. I'm pretty sure it's not. I could double check, I guess. Test. I'm pretty sure it's not. I could double check, I guess. Test. Yeah, I'm not sure. There must be something wrong with your audio or something. Because it's definitely not on me. It's something on your end. Maybe you're glitching out on your phone or something. Not sure. I'm not sure, my friend. Not sure. Just watch your stream. I just did. I just did, brother. And I have confirmed that it must be your issue, not mine. Unfortunately. Did I solve this question? Oh, no, I didn't. Oh, I think I tried. Oh, I remember I tried It's fine. No worries. Okay, so I tried solving this question. I remember this question had some like edge cases. Yeah, I'm not echoing. You have it in 2 tabs. Nice. Nice. Yeah, I don't think I would have duplicate audio. Homa Figma. 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 It's okay. It's okay. You're good. Okay, given a okay, so let me remove all this logic again. So this problem, write a function to insert a value. So basically, somehow you're supposed to know, I guess, about all the edge cases, which is apparently case 1, which is, let's see, the node just has to fit between, right? I've just started Java. Can we do it together? I'm sorry. I think you might need to find a different partner because I don't code in Java and I'm not interested in coding in Java, unfortunately. Insert node or insert val and cur. As long as we meet this criteria, we know that we have to fit this in, right? So for example, in this case, is 3 and 4. So in 3 and 4, is it between 2? It's not. But even this 4 and 1, you could say, oh, it is between 4 and 1. However, we need to make sure that 4 is actually less than 2, which is not. So in this case, this 1 is less than 2, and it's also less than 3. 2 is less than 3. Is Java a good language to study? I mean, Java is definitely relevant for jobs, for sure. Just, I mean, based on what I've seen, I think I would highly recommend Python for interviewing, because I think Python reduces a lot of boilerplate logic, which saves time and gives you more time to actually just, like go through your thought process and code up a solution. But that's not to say that like you could still code up in any language. It doesn't matter. You can code in whatever language you want. Whatever you're most confident in. I mean, I don't think you have to switch. I mean, I use JavaScript for my job mostly. I don't use Python. Like I've barely used Python at work, but I mean, I've just been learning it for interviewing because I know that most people say Python is the easiest for interviewing and the simplest. So take it for what it is. There's no right or wrong answer. You can code in whatever language you want. Okay, case 2, right? We can have a case where the number is like outside, right? So if the insert val is something like 9, I guess how would we handle that? I think sometimes to do a simple task, we have to create a loop. Sure, I guess. Okay, so in this case, we'll actually, if we ever hit a case where is this during our while loop or is this at the end? Even 0, like let's say it's 0, because the 0 would have to be fitting in the 4 and the 1, right? So I guess if we ever reach a case where the previous is greater than the cur. Can it be equal to? I guess you could just have like only 3s or only 1s, right? Which in that case, like, I guess that's case 3. Just insert it anywhere. If 1 or 2, we can hit. If we don't hit case 1 or case 2, then we can just return. We can just append it anywhere. So I guess like we could just append it at the head. It doesn't matter, or insert at the head. And at that point, let's see. Is there? I feel like there was one more case I was missing, but maybe not. But our case 2, I'm just trying to make sure if this is valid. So if we ever meet a point, because like, because let's say it's, actually, is it guaranteed? I mean, it depends where we start. I mean, I guess if we started at the 4, right? Because I'm thinking like, what happens if, how do we know that we need to add it to this between? I guess if it was in between, like, let's say the number was like 2. If the number was 2, then the number has to be either greater than this last number or has to be less than the next number. I think that's the condition, right? So if previous is greater than cur and prev is greater than, and the insert is greater than prev, or the insert is less than the cur. I don't know what a node is. Maybe I would be in a string of arrays because I'm just a beginner. I mean, you'll learn it. You have to learn what linked lists are. I don't know if you've ever gone through data structures, but you're gonna have to probably go through a course on data structures and algorithms, or just, you know, you gotta study it online somewhere. There's plenty of resources online. You could even ask ChatGPT on how to study for it. All right. So why don't we go through this? Technically we don't need to call it prev because we always have something guaranteed. We can just refer to the next node as cur.next instead of like prev and cur, right? So cur.next. And we'll just call this cur, and all these curs will be cur.next. And cur.next, and all that cool stuff. All right, so cur is equal to head, right? So if we have our cur equal to head, so while what is our exit condition though, right? How do we know that we've gone through the whole loop once? How do we do this? I forget. How do we end? How do we get out of this loop? Because we just need to loop through it once to confirm whether or not, you know, we need to add something or not. while cur is while cur we just say while cur dot next is not equal to head. If we say while cur dot next is not equal to head, so we'd say we'd go through this, then this, then this, but we'd stop here though, and we don't process this, which doesn't seem right. We can stop and start from the back. I think you're probably way too I think you need to study a lot more before you do this problem, if I'm being honest. I mean, this is a linked list. There's no such thing as like, well, I mean, I guess you could always go back to the head. But linked lists are always one directional, you know, unless it's a doubly linked list, but usually with these problems it's a single linked list. So you can only go in one direction. But yeah, I think you should just study up on the fundamentals, if I'm being honest, and start with like two sum or something, you know, and then work your way up to like the harder concepts. What the hell is our condition though, right? While cur is, do I just say while cur is not equal to head? Cur. I don't understand what my exit condition is. I'm stuck on this. I don't understand. I mean, in essence, I'm just saying when I start here, I want to end here. But how can I say I end here without referring to next? While cur dot next is not equal to head. We do this. Go to next pointer. But then at this point, we're saying cur dot next is equal to head, so we stop here. Yeah, I'm thinking of it as an array. It's okay, you don't have to apologize. But yeah, it's not an array. You can't treat it like an array for this problem. I guess it's a bit misleading because it looks like an array, but it's not really an array. I give up. I don't want to waste too much time. I don't understand. Where is the question? Insert into a circuit.
Nobody likes a cracked windshield. What was that? No. But you can go to safelight.com and get it fixed now and pay later. Awesome. SafeLight can come to you for free. Don't wait. Get it fixed now and pay later at safelight.com. Safe Light Repair, Safe Light Replace. Wix. One platform. Any website. Unlimited creation.
All we have to do is just create a new node, we'll just create a new node and then return that, right? That's our answer, right? We just have to create it and then link it to itself, right? So we kind of have like a cycle here in the node itself. That's the most simple case. Easy peasy, right?
The head is null. That is okay. I guess that's first case.
Right.
Sure.
The second case is that we insert somewhere inside of it, right? Insert into the linked list. So, this, if we go back to our example where we had 1, and I think it was like 3, will always be greater, right? That's the point where our linked list diagram here is that we insert some, because remember the linked list needs to be circular. So we're going to say new head dot next eternity. So we're going to say while cur dot next does not equal to head. So while
wait, I was right though.
we haven't completed our full iteration through the linked list, we need to do some work here. So the
I said that. Wait, so why does that work though? I thought that wouldn't work. That's what I said. While cur.next is not equal to head. Okay, hold on. But that's the thing though, right? Like, once we're here, right? And we do the cur is equal to cur.next. Wait. Yeah, while cur.next is not equal to head. Which means we would stop here though. Because cur.next is equal to head. Which means we would skip the 1. Would we not? Am I crazy for thinking that? I don't understand why that works, actually.
The first case we want to take care of is the actual insertion, right? We're going to say while cur linked list, well, it's circular, so we're just going to be iterating forever. We need to actually figure out when we've done one full rotation. So to do that, we're actually going to create a copy of our head and just point it equal to cur, and we'll use cur to actually iterate through our linked list here. And when the value of cur actually equals to head, then we know that we've actually done our full rotation, and we can stop there.
When our value of cur equals to head. Yes, I agree with the value of cur equals to head. We're done. Okay, I don't know. Okay, we'll figure that out later. So while cur.next is not equal to head, sure. Then we know that we haven't done a full loop yet. And just for the sake of incrementing our pointers, we're going to say cur is equal to cur.next. And let's handle our first base case, I guess. You know, there we could have an empty no nodes, right? So if not head, we can just simply return a node of insert val, right? And if we don't have that, if we do have, you know, things to process, then we're just going to iterate through this logic. So while cur.next is not equal to head. So if at this point, right, we'll check if cur dot val is less than or equal to insert val is less than or equal to cur.next dot val. Then we can simply insert it in this logic, right? So so for here, what's up, Hilo? How you doing? If we're here, then we can say so cur.next. Okay, we got to create a temporary variable of cur.next, right? Because we're going to lose this. We're going to override cur.next with equal to. It's actually going to be equal to the node of insert val, and is this valid? Is this right? I guess so. And then this node that we just created, but how can I refer to this node though? Maybe I just call this new node. We're just gonna call this new node, I guess. Yeah. So cur.next is equal to new node, right? And then new node.next is going to be equal to temp, right? So basically what we're saying is if at any point this, like, let's say what we wanted to insert is 2, right? And we're at this 1, and the cur next is actually pointing to 3. So we're saying temp. We're going to store this cur next in a temporary variable because we're overriding this cur next to point to the new node. So 1 points now to the new node, which is node of insert val, which is 2. And then new node.next is going to point to temp, which is 3. So that's case 1, right? And then I think we can break from this loop. We don't need to process anything anymore if we've hit this point. The other case is that we might have a if, right? there could be a case where we need to add it to like, you know, the end or the beginning before the beginning. So like in this case, if we have a 0 or a 9 and it doesn't fall in between any of these cases, the 0 or the 9 would have to fit in that, you know, case, the case that we start the loop, right? So if at any point cur.val is greater than or equal to, no, it has to be greater than, right? Cur.next.val, and insert val is greater than cur.val, or maybe I should say it's greater than or equal to, because if it was another 4, we still add it to the 4, right? Or insert val less than or equal to cur.next.val. Then I don't know if this is necessary to put in parentheses, but I'll just do it just in case. And we will again do the same thing. We're going to copy this logic, I guess. It is duplicated code, which we could probably, you know, create some sort of other function and make it simpler. But just for the sake of time, I'm just going to keep going. But by the point, like by the end of all of this, we reach the final case, right? So case 3, we can just simply, can we just return here? Maybe we can just return here, because we should return. You know, what do we return? We can just return. What do we return? Head. You should return the originally given node. Yeah, so we can return head in these cases. And in this case, we still haven't returned, which means we've hit our final case, right? So we can simply just, again, it doesn't matter where we add this stuff. We can just do this again, I think. And okay. Oh. Right. New node. Okay, you know what? Let me just do it like this. New node dot next is equal to new node. It'll just point to itself. The tail does not point to its head. What? Oh, head. Got it. All right. It's a little slow. I must have not been optimal the way I wrote it, maybe.
Need to handle what happens. At this point, we just want to return the head. Cool. So if neither of these statements fires here.
Oh, I combined it into one if statement. That's funny.
Whoops, I think this actually needs to be indented. Yeah, there we go. Okay, cool. If neither of these triggers, then, well, even if they trigger, actually, no, we would return head here. So if neither of them trigger, we need to move on to the next element in our linked list. So we're going to say cur equals to cur.next.
No, I feel like I wrote this pretty well. Wait, but why didn't he do the temp stuff? Cur.next is equal to new node.
Next, and we're going to move our iteration because the new node, and then what is the, we can put it here, we can put it value of our node is actually greater than cur.next.val, right? Because it's circular. Therefore, what we're going to do is we're going to say if cur.val is less than or equal to insert val, which is less than or equal to cur.next.val, then we can actually insert the value between cur and cur.next. So we need to create a new node that we're going to insert, and we're going to say it's going to be a node with value insert val, and its next value is going to be whatever the next node is, cur.next. And now we need to actually update the current node, its next, right? Because its next value is pointing to whatever cur.next is, but we need it to be pointing to this new node now that we created, and we're going to be inserting it there. So we're going to say cur.next equals to new node, and at this point we've completed our insertion, so we can simply return the head, which is remember what they're actually looking for. All right, now we have the other case where we need to handle what happens at the edge of our linked list and whether or not we need to insert something there. So remember that we know that we're at the edge if the current value of our node is actually greater than cur.next.val.
Wait a minute. How is he able to? Oh, because he inserts cur.next. Oh, I see. cur dot next. Oh, I see. It's a little more optimal, I guess, in the sense that, man, it's always so important to like make sure you understand like what you're able to do with the problem in the problem. Because in this case, you're actually able to utilize so the reason why he doesn't initiate it, you know, like anywhere. So like I did it globally kind of. But the reason you don't do it here is because when you do it here, you can say, you can declare the next. You can just declare the next value, which the new node would be cur.next, right? That is what the new node should be pointing to. But cur.next should be, or I don't understand actually. Yeah, that makes sense. And then you overwrite cur.next to new node, right? That's the reason. That's actually kind of tricky. I feel like it's not like that intuitive, but I guess it works. Like this works. Case 3, same thing here. We can just create it. It's all necessary. So new node is equal to node of cur or insert val, and then cur.next. And then new or cur.next is equal to new node. Intuitive or not? I don't know if it's that intuitive. Is it intuitive? It's tricky. It's tricky. So this logic is saying the next value is cur.next, so you can just overwrite cur.next with the new node instead. So technically they're both, so this line, this new node, I think what we're basically doing is that, you know, you have your whatever, you have your circular linked list, whatever, right? So what I'm basically saying is I create a new node, which says something like, I'll just call this n as new node. This new node points to this, which also is whatever the current is pointing to, because we declared that here, right? So node of insert val pointing to the cur next. But then we're also saying in the next line, cur next is actually not going to point to this anymore. It's going to point to the new node, right? So now it would just look like 1 to n to 2. So this is basically the same thing as like inserting a pointer. Impressive. It is impressive. I would not have thought of that. That is impressive. Now the question becomes, okay, back to my original question, which was, I guess the main thing that I was stuck on. How, okay. Why does the while condition make sense? Because I initially thought that if you're going to end, if cur.next is not equal to head, we would stop one node too early. How are we able to correctly determine if we have fully executed a cycle? Mm-mm-mm. Keep going until the next pointer would wrap back to the head. When that condition finally fails, you are sitting at the last node. Oh, so we don't ever hit it. Is that what it's saying? I guess so. Um, hmm. There are multiple suitable places for insertion. You may choose any place to insert the new value. So we are skipping, so we are not processing the last one. Okay, so you're not stopping one node early, you're stopping at the last node, then processing the last gap in the post. I see. I see. Okay. But then intuitively, okay. Okay, I see what you're saying, but I don't know if it's that intuitive to know that the post processing loop is to handle the last case. Like, how is not processing the last node? How does it make sense when, like, how can we guarantee that it will never hit case 1 and case 2? That I don't understand. Yo, why is ChatGPT so freaking slow, man? Your loop scans every gap except the last gap, correct. When the loop ends, occurs the tail. Oh my god. Wait a minute. That is so clever. Like, how? Okay, I think I get it though. It's just like, it's so gracefully handled. I just don't understand how you're supposed to think of it that way. It's crazy because I think the whole reasoning is because this, you actually aren't processing this node because if it belonged here anyways. Okay, so we have our 3 cases, right? it should be in between, right? So even if we don't process this one and the number was 2, this case 3 adds it in. So this case 3 actually handles case 1 as well, technically. And then case 2, even if case 2, let's say the head was actually here and we didn't process, and when we're here, right, we'd stop the loop here. Oh wait, no, sorry. No, we'd stop the loop here, which also would be handled by case 3. But also case 3, well, I should put a case of its own. Like, in the case that we should be inserting it anywhere, that would be handled by that case as well. That is just crazy. I don't know how you're supposed to know that. That's just crazy to me. It's just too gracefully done. How? Yes, whatever this person just wrote is what I just said. Oh my goodness. Oh my goodness. That is crazy. It's just too graceful. Just cannot, words cannot describe how graceful it is. It's just gracefully done. Just gracefully handle all edge cases. And the final node creation is the catch-all case, which will be handled. I see. So what you're saying is we might actually not even trigger case 1 or case 2, but we'll still handle it, the case 1 or case 2 case, if it happened to be the last node that we didn't process. So it's basically like a catch-all case, because it also handles the case that if all the nodes were the same value, then we would just insert it anywhere, which we could just add it at the end anyways. Oh my god. Insane. Insane. Why does ChatGPT look like its responses are a bit different than before? All right. Should I do one more? How many questions have we done so far now? 55? When do I stop? Do I stop at 100 questions? Do I just memorize the top 100? Maybe not memorize, but like go through them over and over again. I think top 100 will be good. My recruiter said 50 is good enough, but I feel like 50 is not that many. Wait a minute. Add 2 numbers. What? Oh my god. Now I actually don't know the order of which I did things in. Which one did I not do? Okay, this one I don't think I... Remove nth node from end of list. Have I done this? I don't think I've done this. All right, another one. You wish for some rain? Wait, why? Why do you need rain? Okay, given the head of a linked list, remove the nth node from the list and return its head. Is it guaranteed that we'll find it? And also, this doesn't seem that hard of a question. Unless there's a trick to it. So cur is equal to head, right? N is equal to 2. Remove the nth node from the from the end of the list. Oh, okay. It's not as simple. I thought, okay. I initially thought we could just traverse through, but it's actually the nth from the end. So if that's the case, could we not implement tortoise and hare algorithm here? All right. Can I get another Excalibur session? Just kind of want to... Bro. I want a new one. Excalibur. I want to draw. All right, so... Let's zoom out a little bit. Okay, so I was thinking... In my head... So we're done with this problem. Done with this. Okay. So I was thinking we could just do something like tortoise and hare. Could be wrong. Because my thought was, all right, so like we have 1, goes to 2, goes to 3. Let me get my trackpad. Never mind, I found it. Okay. Gonna be golden. Get it to n minus node and point it to n plus node. I mean, yes, that's basically what it is. Basically what it is. But it's not as simple because you got to start it from, but it's the n minus, it's the n from the nth end, not from the end start. A calm tablet. It was not as simple of a question, which I initially thought it was simple like that, but it's not. Software. What the hell is my model? I don't even know if I have that info, do I? Latest Wacom driver. Or select your product category. Find the length of linked list node and then remove. Yes. Yes, that is 2 pass. I was wondering if you could just do it 1 pass. Which I think you can with tortoise and hare, I think. I was trying to draw my thought process. I have this one. I think I have this Bluetooth. There's one with Bluetooth, so I don't need a wire? Damn, bro. It's a little more expensive, but whatever. I barely use this thing anyways. Software. What's this for? It's for my tablet, but I think I need software to download like the drivers and stuff. I mean, it's for art. Yeah, it's mainly for art, but you can also use it to just kind of, you know, you can just write on the computer, which is also convenient. No, I'm not an artist. Like, for example, like I want to draw on this, but you know, it'd look way better if I could just communicate my thoughts more effectively and draw better if I just had, you know, an actual tablet. So in these moments, it comes in handy. Bob Lee. I think I could just download this. I'm pretty sure this is valid. Yeah, I think this is fine. We'll just download this, install it, see how it goes. I think this is going to be my last question, chat. So I'll probably be done after this question. Got a nice like 2.5 hour study session going, which is not too bad. I also like took a break, not only because of my cluster headaches and well, I don't know. I think I probably would have not taken like more days than how many I took if it wasn't for the headaches. But I also wanted to take a break because I felt like I was just starting to become fatigued at just studying too much, and I feel like things were kind of I feel like my brain was like becoming mush, and my decisions and stuff like that were, you know, not as optimal. So it seems like they need me to restart my computer, which is a little bit annoying, I must say. But brain is shrinking. I don't know if it's shrinking, but that's annoying. Whatever. I guess I won't restart my computer now. Oh, but it works. There you go. It works. Okay, we didn't need to restart it. They baited us. All right. So, okay, back to I guess this thought process. So, what's the example they gave us, right? They gave us so they gave us 1 goes to 2, goes to 3, goes to 4, then goes to 5. And our n is equal to 2, right? So if our n is 2, like our slow pointer, I'll denote it as slow and fast. We start both, we'll start slow and fast together, right? And then slow goes here, then fast goes here. Wait, I don't even think that works. Right? Because we don't even know how long it is. But technically, you could reduce the half of the linear time if you did it this way. Maybe. Actually, I don't even know if that's true. That's not true. I think techno, your solution is probably the optimal way to do it. I don't even think this works. So you just gotta, I guess, scan through the whole thing once, right? So scan through this whole thing once, find the length, which is 1, 2, 3, 4, 5. So we find that the length is 5, right? Or yeah, we say 5 and then n minus 2. I think we do n minus plus 1 because 1 basically means the end. So just got to keep that in mind. So 5 minus 2. So this fifth position minus 2 plus 1, which denotes we have to go 4, right? So from here, from the start, we go 1, or we start at 1. So 1, 2, 3, 4. And then we, well, technically, oh, actually, maybe we, no. We don't want the plus 1 because if we say 5 minus n, which equals 3, then we'll actually end it at here, which is where we want to be, so that we can remove this one and then point to this one instead. The follow-up says to do 1 pass, so maybe it's do, oh shoot. Okay, yeah. 1 pass. I really do think it does have to do with a slow fast pointer approach then, if it's 1 pass, right? So like if I just explained that thought process in meta, they would be like, can you do better? Which I would probably think like, let's say we have a slow and a fast pointer. Well, yeah, I think, okay, so I think n actually determines how our distances, right? So it's not really like a fast pointer, but it's just like a 2-pointer, right? So like pointer 1, so we could just mark it as 1 would be at the start, and then we add 2 to it, right? So we'll do a next 2 times, right? So we'll skip 2, and then we'll basically be at 3 now, right? So 1 is at 1, and then 2 is at 3 because we performed the dot next n times, right? So at this point, we say 1 dot next is 2, 2 dot next is 3. So at this point, we maintain 2 pointers, right? And then all we have to do is simply, while we go until the end of this linked list, right? We know that once we're at the end of this linked list, our pointer 1 will be at the correct position, right? Because if we move this over 2 times, right, this pointer will be at 5, and then this pointer will be at 3, right? And then we can simply just perform, the simple, remove at that point. So that solution would be a 1 pass. And I think that is the correct solution. So why don't we just code that up real quick, shall we? Let me just like write down some of my thoughts to just gather. So 2 pointers, right? So 2 pointers, and then we'll have, and then while pointer 2, and then remove node P1. That's basically like the whole logic, I would say. And this is 1 pass. So we have pointer 1. But I mean, I don't know. Can we also, I don't know. Can we assume that, the n is valid? I'm going to assume it's valid. I mean, I'll probably clarify that with the interviewer, but we'll handle those edge cases, I guess, if, it's not valid. But let's just say it's valid. If it's valid, then it is what it is. N is valid. Yeah, but I'm saying like, what if there's a case where it's like N is like 4, but you only have like 3 nodes? I'm going to assume, I'm assuming this problem made it so that, every input is valid with an N, like the nodes. So P1 is equal to, I guess we'll denote it as head, and then P2 is also equal to head, and we will say should be valid. Yeah, I'm assuming. Otherwise, I feel like there's too many edge cases, and this problem would probably be hard. So for I in range of n, we can simply just do a P2 is equal to P2.next, right? This will basically say, right, from our original example, we start P2 here, right? So pointer 2 is here. For I in range of n is 2, so we're going to do this 2 times, right? So P2 is equal to P2.next, so we'll move this pointer here, and then we'll do it one more time because n is equal to 2. So now our pointer 1 and pointer 2 are correctly distanced apart, and so we move both pointers together. So while P2 is I think oh, wait a minute. We gotta be careful. We gotta say while P2.next, right? Because we don't want to say while P2, because if we say while P2, then we're actually going to end P2 at this pointer, right? Which we don't want. We actually want to end the P2 here. So we have to check the P2.next. And we'll stop the pointer at this point if we don't have a P2. So in this case, we can say we're just simply incrementing pointers. This part is like kind of easy, I feel like. P1 is equal to P1.next and P2 is equal to P2.next. By the end of all of this, our pointers should be configured properly. And then at this point, we want to remove the next from P1. So P1.next should be equal to P1.next.next. Right? So what I'm saying here is that at this point, where P1 is set to 3, and I'm saying P1.next is not equal to 4 anymore. I'm saying look at the .next.next. So P1 is now equal to P1.next.next, which is 5. And at this point, I think we can just simply return the head. Frick. Has no attribute .next? Do I say while P2 and P2.next? What the hell are these edge cases? Oh, that's right. Wait a minute. I thought this question was easy, but it's not. It doesn't work as easy as I thought. I feel like I have to handle the edge cases better. Is this an edge case? You could just point to none. What if I write it like this? Or like this? Okay. Wait a minute. We need a dummy pointer, I think, for this problem. Are you serious? There's an edge case if fast reach is null. Wait, do you need to do this with a dummy node techno or no? Or can you just do this without a dummy node? I looked at my solution from a year ago. Yeah, but did you use a dummy node or no? I need to know. Oh, you didn't? Okay. If the fast reach is null. Oh wait, so it can be empty, is what you're saying. You're saying the end could be like, if fast reaches the end, return head dot next. I don't even understand what that means. Oh, hold on. All right, you know what? F it. I have to look up the solution. I tried my best. I failed.
Imagine being able to build anything just by thinking about it. Meet base 44.
Hey everyone, welcome back. Let's write some more Leetcode today. Today, let's solve remove nth node from the end of a list. So we're given definitely a possible solution, but it requires reversing the end of the list. Like a lot of linked list questions, we can use 2 pointers, but how are we going to make use of our 2 pointers? And the right pointer when we do that. It's at the end. So now our right pointer is at null, right? It's at the end of the node. If we want to delete by 1, it's going to be shifted again, and our right pointer is going to be over here. So now we're just going to keep shifting our pointers until this right pointer is at the end of
That's exact. Oh, at the end?
the list. And watch what happens when we do that. So we're just going to be shifting each pointer by 1. And this is going to make sure that the space between these pointers is exactly equal to n, which is 2, right? So now we're going to shift by 1 again, making sure that the gap between them is still 2. Now we're going to shift 1 last time because right is almost at the end. So now our right pointer is at null, right? It's at the
Oh.
end of the list. It can't go any farther. And our left pointer is exactly at the node that we want to delete. And the reason is because, remember, the offset between these two is n, making sure that we have the node we want to delete. Now there's only one problem. We have access to the node that we want to delete, but we want to delete it. How do we delete it? The only thing we have to do is take this pointer, cross it out, and then reassign it over here, right? Once we've done that, we've gotten rid of this node. So the problem is we're at this node when really we want to be at this node if we want to delete this node. And this can actually be solved by another pretty common technique, the dummy node, right? So we're going to actually have another
Dummy node, I said that.
node that we insert at the beginning of this list that we don't really use. And the main thing that's going to happen is instead of our left pointer being initialized here, we're actually going to initialize it at the dummy node. So left is really going to be initialized here, and our right pointer, though, is still going to be initialized over here. So in reality, when our right pointer reaches the end of the list, we will have a left pointer at 3, and then we can update its pointer, removing this node that we want to remove. And to return the new linked list, all we have to do is take our dummy pointer and say return.
Let me see if Cracking Fang does the same thing. Does Cracking Fang not even solve this problem? It's a linked list question? Bro, you think I'm stupid? I know that. I know it's a linked list question. Dude, look at literally what I've been drawing. Okay? I'm just trying to figure out why it's wrong. I know it's linked list. I'm not dumb. Why do you think I'm dumb? I'm literally watching a video on why I don't understand why my solution doesn't work. And I'm seeing if there's better ways to do it. Whether or not I need a dummy node or not. Calm down. All right? Calm down. Where's coding with Minmer? I mean, this guy's smart too, I know. Nick Way.
Surprise, it's me, your oil change light. Here to ruin your day. Remember that last
Go, have a counter and go up to 2 though.
because we don't know the length of an extra loop, one pass loop. So let's just do the one pass version since it's pretty easy. So what you're going to want to do is you're going to want to have a slow pointer and a fast pointer, and the fast pointer is just going to go up to the position +1. And then you're going to let the fast pointer go to the end of the list while the slow pointer starts at the beginning from position +1, and slow pointer will end up at the position ready for. So just a little bit of trick math to get to the position ready for the one you want to delete. So we'll make a dummy head, which will be a...
They all do dummy head. I think dummy head is the way to do it. I'm surprised you did it without a dummy head, Techno. I feel like a lot of these problems you want to do a dummy node.
Hey y'all, and welcome back to Coding with Nimmer. 7, I1. Yes, I'm aware there's a node. Okay, so what do we already know? We know that there's a buffer of 2 nodes from the end of our linked list node, which we know to be true, or to be next.
This guy also has a dummy node. You can send the solution? Sure, you can. I mean, I don't know if you have like way more lines though to cover edge cases. I think the point of the dummy node though is to like handle the edge cases well. So let me just create a dummy node here. Dummy node of list node. I don't think we have to initialize anything, and then dummy node dot next is equal to the head, right? And we can just say P1 is equal to dummy node, and P2 is equal to dummy node. Actually, P2 is also equal to dummy node, and then for I in range of n, P2 is equal to P2 dot next. However, in this case where we do the dummy node, so if we have a dummy node here, right? Just call this like D. Okay, let me just erase a lot of this stuff. Let me just remove all this. Okay. Okay, it's all good. So we have 3. All right. So we start P1 here, right? And then we're moving it. But if we just move it 2, right? Like, so if n is equal to 2 in this problem, which n equals 2, so we do P1 go twice, or P2, sorry. P2 goes twice. P2. This is still incorrect, right? Because if we move 1, 2, 3, 4, we go 1, 2, 3, 4. It's still wrong. So we actually need n plus 1 is going to be the correct way. We're going to have our thing set up. Yeah, I'll check it out after I'm done with this. So while P2, right? Because we are actually going to the end, like apparently, I guess. So P1 is equal to P1 dot next, and P2 is equal to P2 dot next. So actually, what happens at there in this logic, P1 is now here, and P2 is now here. But technically speaking, like I feel like even though what I just did is exactly the same as what just happened, right? Maybe not though. Actually, it's not. In the cases where it's just things like 1, right? In the case where it is just like 1 and we do have a dummy node, right? P1 and P2 and n is equal to 1. P2 is actually 1 plus 1, right? So P2 is 1 plus 1. So P2 actually already ends up here. So, and then I say while P1. Oh. Yeah, this handles the edge cases way more nicely, I guess. Because in this case, we're saying, oh, the dummy node. Yeah, then the dummy node is just equal to, right? Because at this point, we are at the correct position, right? So then all we can say is P1 is equal to P1 dot next is equal to P1 dot next dot next. And then we could just return dummy node dot next, right? Oh my God, it's beautiful. It's just so clean and beautiful. All right, now we got to see your solution. Where'd you DM it? to DM it in, okay. Wait, but this is also nice too, though. Wait, fast, slow. If not fast, return head. I see. If not fast, return head dot next. So mainly the difference is that I guess technically you have like an extra edge check where it's if not fast, return head dot next. So what you're saying is, okay, let's go through this example, right? This one example, and n is equal to 1, right? And you're saying that you start both slow and fast. So slow and fast are both at the start. And then n is equal to 1, right? I see. I get it. Slow is equal to fast. Okay, so fast actually goes 1, right? So fast is actually none. So this is why this would hit the if case, right? If not fast, then all you're doing is return head dot next. I mean, I feel like it does work, I guess, but it doesn't follow the pattern, if that makes sense. I feel like the dummy node pointer solution is better in the sense that it's consistent across the board, if that makes sense. You know what I mean? Like this edge case, we're technically just like, I don't know if I want to say it's jank. I mean, I think it's still valid. I don't know. Like, I'm sure an interviewer would still like accept this, I think. Because you're saying if not fast, return head dot next, which this edge case is for length of linked list is equal to n. Okay, but let's say n is 3 and the linked list is 3, right? So you have 1, 2, 3. So then slow, fast. Fast is 1, 2, 3. So fast would be at the end, right? And slow is at the beginning. So then all you just say is if not fast, return head dot next. Well, how does this work though? I feel like this shouldn't even work. Because if we're saying remove the third, oh wait, oh, because you're removing this one. Oh, that does work. That's true. Oh, so if at any point, because I guess you know that anytime fast is at the end, you know that n is equal to the length of the linked list, so that you know you always have to just return, like remove the first element, so you just return everything after it. I see. That makes sense. That makes sense. I mean, I guess you could do it both ways as long as you can justify both reasons. I mean, that makes sense. I don't know though. I will say I do feel like a lot of people solve this using dummy pointers though, like these types of problems. Because I feel like it's just easier to have a pattern. This is kind of just like a,
With the release,
I feel like it's kind of, I don't know. I feel like that intuition would be kind of hard to figure out during an interview.
Hey everyone, welcome back.
I can't lie.
Now last two, but I want to set its next return dummy list. We just want to remove a node. So our solution, pointer to 2.
While n is greater than 0 and right. I mean, this is also valid, but I wonder if this way to write it is better. While n is greater than 0 and right. I should eat food first, I feel like. I should eat food first, I feel like. Before I end. Otherwise, it'll be too late. I feel like if I just end and then eat. No dinner? Yeah, I was gonna eat dinner now, I guess. I mean, this is not like I mean, let's ask ChatGPT. Is my for loop jank or optimal or completely fine? Is the +1 mandatory with the dummy node? Oh, I mean, I understand why. I feel like a visual helps a lot. All right, I'm gonna eat. Should I just eat some snacks? So then I'll save a Chipotle bowl for another day. Save some money. Just save some money. Yeah, it's a string cheese. Did he Valo already? I didn't do my Valo dailies, but I think my brother is playing actually. Let me check. Valo session. We'll see. It's getting late though. Of course, I'm sitting at the top. See what they're playing comp. I'm not trying to play comp right now. Must be lonely at the top. What is this? Let's watch this video. The Zuck. More layoffs coming? Question mark.
So I just want to preface this video by acknowledging that this isn't exactly news. As a matter of fact, it's actually been published since about late May, and I'm just a little late to the game. We just completed the most recent round of mid-cycle performance reviews, and I figured better late than never. It's not so much the news that I want to discuss, but the implications. As you've probably read in the title and the thumbnail, the video is about the increase to the number of employees Meta will now place in the below expectations bucket. Across the board, the target used to be 12 to 15%, but now it's been bumped to 15 to 20%. While overall not a massive increase, I think it paints a picture of what's to come at Meta and where the company's going. For some context, I believe in what must have been at this point 2021 or 2022, the company switched to doing yearly performance cycles. They used to be every 6 months, but it was increased to 12 to quote-unquote allow engineers to focus on more long-term impact. This definitely was not the end result, and people still play the same PSC games as they did before, but that's a whole nother video for another day. While official ratings are only provided at the end of a year, we still do a mid-year check-in as a pulse check of how the year is going so far. We still go through the same process of requesting feedback and writing a packet, but now you can only get one of 3 ratings: below expectations, at or above expectations, or significantly above expectations. These ratings are meant to be an indicator of the direction that you're trending, and officially they're not meant to affect your year's end performance rating, but the reality is that this isn't the case. It's not meant to lock you into a particular rating, but in practice, it seems like it makes it very, very difficult to break out from the rating that you're trending towards if you get a below expectations. You damn near have to bust your ass and have a crazy strong H2 to get anything higher than a meets all. You can definitely recover the situation and not get a meets most, but it seems like they're using BE ratings from mid-cycle as a negative towards your end year rating. All of this is technically speculation on my part from what I've gathered from anecdotal evidence of others, so do take it with a grain of salt, but I definitely do lean heavily towards actually believing this than the official company narrative. Now that we have some basic context of how mid-cycle evaluations work, let's return to the overall theme of the video, which is the increase in the percentage of people getting below expectations ratings. This really isn't something surprising given the recent history of the company, and it's really to be expected. I think we're starting to see a shift from the company to be more ruthless and out for blood. The days of cutting people some slack and having some built-in flexibility in the system seems to be fading out. Maybe it's the pressure to win the AI race, or we've just gone full megacorp profits over everything. Regardless of what's actually motivating the change, it's obvious and apparent to anyone working there that they're tightening the screws. The heat is being turned up and employees are being squeezed that little bit harder. Partly from management and partially from the social pressure of not wanting to fall behind and thus forcing ourselves to work more and more. I don't think these changes are temporary, it's just the norm now, and I'm also not convinced that creating an environment where every employee essentially has a sword dangling over their heads will actually net something positive in the long term. But the days are here where you can just hire and fire at the drop of a hat, so it doesn't really matter. Projecting this forward, we're probably going to see another round of layoffs in early 2026, a yearly cull of the bottom 10 to 15%, similar to what Netflix
Bottom 10 to 15%.
does or did. I'm really not up to date with their hiring practices these days, but there's now a constant fear that if you mess up, stumble for just one half, that could be it, out on your ass and unemployed. As someone who has been at Meta for a long time, it's not nice to see the company go down this road, but here we are. I don't think things are going to change. People often ask me at the end of interviews what it's like to work at Meta. Is it still a nice place? I still default to my usual answer of yes and can list off some of the pros of working here, but the more I think about it, a lot of what the company used to be has eroded away. It's lucky that the stock has also been rising in tandem with all of these increases in performance and layoffs, otherwise the situation would truly be dire. Rising pressure and falling compensation. Isn't that a recipe for a good workplace? I suppose I want to end with the question of what is one meant to do in this situation? How should one navigate these strange times of the company? Well, I
Just be a K-pop idol. Do you understand how much harder? I actually think it's arguably harder to be a K-pop idol than be a software engineer. But I guess it also depends what you define as harder. But I mean, both are. I mean, it depends. Like everything depends, right? Like, if you want to be at the top of anything in life, the amount of work will increase. It's usually almost always correlated. You know what I mean? Like, your life is not easy as a K-pop idol, and your life is not easy as a top software engineer. Which makes sense because usually money is tied to being at the top.
suppose that we should just focus on the things that we can control. Focus on playing the game as well as you can. And it's a shame that people need to do this in order to get by, and that it's easier to just game the system than to actually do good work. It seems that if a project is not flashy enough or high visibility enough, people just don't want to do it. And ultimately, that's not a sustainable thing from an engineering standpoint. Shipping loads of terrible code just to chase impact, consequences be damned. But if the alternative is a bad rating and a severance package, then you already know which road engineers are going to take out of self-perseverance.
Yeah, I agree. Like, it's not fair if all people are doing to not get fired is legit just look good on the surface. Like, even if it might not be the most like exciting thing, but you're still technically doing like meaningful work, but the company, I guess, won't view it the same way, and you get fired for it. Of course, everyone's gonna just go for the thing that's just, you know, the flashy or the hot thing to work on, because I guess on paper it might look nicer, which is annoying, I guess. So it just kind of comes down to like, dude, I feel like team select is legit like your decision to whether or not you kind of solidify your place or you just kind of grief.
There's still a treasure chest of information and experience to be gained in meta. For those that want to make the most of the opportunity, it's there for the taking. It's still a top company with fantastic opportunities for development, both technical and career-wise. But we do have to understand that the game is different now. The rules have changed, and we need to adapt or we'll be left behind. It's getting harder and harder to get by. The water is rising. Things are cutthroat, people will throw each other under the bus, and engineers are being just that little bit more defensive about collaborations and sharing their projects. Everyone
Damn, that is savage.
wants to hoard the impact for themselves. Like I said, the screws are tightening, but also, as they say, if you can't take the heat, well, get out of the kitchen. I think I'll leave it there for now. I'll continue to keep an eye on the situation and report back if something of note changes. We're playing a high-stakes game now, but I know I'm not the only one who's thinking this. Sometimes just knowing others are in the same boat, and they're thinking and feeling.
So people are resorting to gatekeep information or just, you know, gatekeep any progress that you can make, you know, for your own self-gain. I mean, understandable. It's a dog-eat-dog world out there, and it's just survival of the fittest. You know, everyone's in it for themselves at the end of the day. Why should they sacrifice their own or jeopardize their own position just to help you out?
The same thing is enough to push us through the tough times. To all of us at Meta, we're all in this together. Good ratings, bad ratings, we're all in the same ship. Let's smash it in H2 and see what Zuck has in store for us.
The Zuck. Dude, videos like these just make me wonder, like, should I just stop studying and go back to grinding content? I don't know.
Navi, welcome to the show. Yeah, nice to be here. The CEO of Amazon Web Services, or AWS, Matt Barman, just said,
There are people who don't want to share their tasks, so they make the most impact. Yeah, it makes sense. I mean, I think even people in my current company do that. Like, the people higher up they just do things to look busy, or dude, like some of my uppers are like so shameless, like legit just copy pasted a chat GPT response in the chat. No shame. Like even like the formatting with like the headers and the bullet points, it's like, bro. You have no like, you have no shame. And apparently somebody upper decided to like delete the documentation that somebody else wrote and just reposted it so that it looks like that person wrote it and they get the credit for it. That is extreme shameless. Like, what are you like? Why is it that serious? I don't understand. It's disgusting. Why are people like this? I don't even understand. I mean, if it happens at companies where, you know, you're not even getting paid that much compared to these other top tier companies, like I would assume it's even worse in the you know, in the higher tier companies. Our marketing team does that too. You know, one of my engineers told me like a sign that people just copy paste GPT is like look for the dashes. If people have dashes in their responses, that means it's ChatGPT. I never thought about that, but that is true though. When ChatGPT talks, ChatGPT has a lot of dashes. It's not like, if you like, any normal person doesn't really use dashes in like English language. I feel like it's not that common. I feel. But like if you see dashes like this, you know like somebody GPT'd it. I was like, damn, that's true. That's kind of smart. Oh, I always change to comma. That's funny. ChatGPT codes are also too clean. Well, I mean, I don't even know if that's a bad thing though. Like I feel, especially with these types of interviews, like at coding interviews, they want you to be clean. So they're basically trying to make you be ChatGPT. But whatever. I'm so glad I went into nursing. Software engineering is brutal. It's perspective. It's perspective. To be honest, if I wanted to chill, yeah, I will say my job right now, it's hella chill right now. That's all I can say. So like, this is why it's all like it's all perspective and like how far you want to climb up the ladder, right? Like if I wanted to chill right now at this very moment and I didn't care about progression, yo, I'd be chilling. But I mean, the way I am though is like I'm a grinder, and I don't think I'm satisfied with settling for less, because I do feel like I want to be the best that I can be and do the most that I can do, you know, given the position that I'm in. So that's why I guess I do more. I don't have to do more, but, and this is all like dependent on the person. And I accept the trade-offs, I guess. Like I know it will be more stressful, but like what am I going to do? Would I just rather sit in my ass all day and just, you know, be middle class for the rest of my life? I could, but I don't think I'd be satisfied with that. No work, all party. Wanted us to comment each code we aren't copying pasting from AI. I mean, I think you could even ask ChatGPT to comment your code as well. So like, I don't even understand like how that's even gonna prevent anything from people doing it. Oh, tennis. I don't know. I stopped watching tennis ever since Federer retired. I only watch tennis because of Federer. All right. Anyways, I'm done, chat. It was a nice chat. I'm gonna end, and I'm probably gonna just, I don't know what I'm gonna do. We'll see, but I might study some more after off stream. We'll see, or I don't know. We'll see what happens. But I'm done for today, I think, and I'll see you guys next time. I'll probably study again tomorrow though. Did I watch WWE? When I was younger, like not really. No, I never was into WWE. It's just weird, and like I watch it. I've seen clips of it now too. It's just like I don't know how people. I don't know why people love it so much personally, but I can never get into it. It's just a little. I don't know. I don't know why. I don't know why people like it so much, but I guess it's just a show, you know. So I mean, I guess I could get it. Yeah. All right. Peace out, chat. See you guys next. I'll probably see you guys tomorrow. I'll probably study again tomorrow. So peace out. Peace out. Much love.